Ground is an electrical connection to the Earth's surface or a conducting body that serves as a common reference point for electrical circuits. This is typically achieved by driving a metal rod or plate into the ground. Neutral is a designated conductor in an electrical system that is maintained at a neutral potential reference point. In a three-phase system, the neutral is the center point of the three-phase windings and is typically connected to the ground at one or more points in the system. The main difference between ground and neutral lies in their purpose. Ground is primarily for safety and protection, while neutral is used for balancing phase currents and providing a reference for voltage. Ground is always maintained at earth potential, approximately 0 volts, while neutral may not always be at 0 potential due to imbalanced loads. Ground is directly connected to the earth, while neutral may be connected to ground indirectly through equipment or isolation transformers. Ground is intended to carry fault currents and surge currents to protect against electrical hazards. Neutral typically carries unbalanced load currents and return currents for electronic devices. The significance of grounding in a power system is substantial. Firstly, safety. Grounding provides a path for fault currents to flow, preventing them from flowing through people or equipment, reducing the risk of electric shock and fire. Secondly, equipment protection. Grounding helps protect electrical equipment from overvoltages and surges by providing a low resistance path to divert excess current. Thirdly, voltage stability. Grounding helps maintain voltage stability in a power system by providing a reference point for voltage levels. Fourthly, neutral current return. In three-phase systems, grounding provides a path for neutral currents to return to the source, ensuring balanced current distribution and preventing overheating of neutral conductors. Grounding helps dissipate lightning strikes by providing a low-resistance path to earth. To elaborate further on grounding, it is important to understand its function within the broader context of electrical safety. The electrical systems are designed with multiple layers of protection, and grounding is a fundamental component of that protection strategy. When a fault occurs, such as a short circuit where a live conductor comes into contact with a metal enclosure, a large fault current flows. Without a proper grounding system, this fault current could energize the enclosure, posing a significant shock hazard to anyone who touches it. The grounding system provides a low impedance path for this fault current to return to the source, typically the transformer. This low impedance path facilitates a high magnitude of current flow, which in turn causes the circuit breaker or fuse to trip, quickly disconnecting the power and eliminating the hazard. The ground wire, usually green or bare, connects the metal enclosures of electrical equipment and appliances back to the main grounding electrode system at the service entrance. This grounding electrode system consists of elements like ground rods, metal water pipes, or concrete encased electrodes, all designed to establish a reliable connection to the earth. The earth itself serves as a vast reservoir for electrical charge, and by connecting the electrical system to the earth, we ensure that the potential of the grounded components remains close to 0 volts relative to earth. This minimizes the potential difference between grounded equipment and the earth, thereby reducing the risk of electric shock. Now let's delve deeper into the role of the neutral conductor. In a typical 120/240 volt single-phase system, the neutral conductor provides the return path for current flowing in the 120 volt circuits. The 240 volts is derived from a center tap transformer, with the center tap connected to the neutral. This creates two 120 volts legs, each referenced to the neutral. When a 120 volts appliance is plugged in, current flows from the hot conductor through the appliance and back to the source through the neutral conductor. In a balanced three-phase system, the neutral conductor ideally carries very little current. This is because the currents in the three phases are 120 degrees apart and, under balanced conditions, tend to cancel each other out at the neutral point. However, in real-world scenarios, loads are rarely perfectly balanced, and the neutral conductor will carry some amount of unbalanced current. This imbalanced current can be significant in systems with a high proportion of single-phase loads, such as office buildings or residential complexes. It's important to note that the neutral conductor is also grounded, typically at the service entrance. This grounding connection is crucial for maintaining the neutral at a potential close to Earth potential. However, the neutral and ground conductors are kept separate throughout the distribution system, except at the service entrance. This separation prevents normal load current from flowing through the ground conductor, which could create noise and interference in sensitive electronic equipment. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. Bonding refers to the practice of connecting all metal parts of an electrical system together to create a common ground reference. This includes metal conduits, junction boxes, and equipment enclosures. Bonding ensures that all these metal parts are at the same potential, minimizing the risk of shock hazards. The NEC specifies the size of the grounding and bonding conductors based on the size of the service conductors. It also provides guidelines for the installation of grounding electrodes and the connection of equipment grounding conductors. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. In addition to safety, grounding also plays a crucial role in protecting sensitive electronic equipment from voltage surges and transients. Voltage surges can be caused by lightning strikes, switching operations, or other disturbances on the power grid. These surges can damage or destroy electronic components if they are not properly protected. Grounding provides a low impedance path for these surges to dissipate to Earth, diverting them away from sensitive equipment. Surge protective devices, or SPDs, are often used in conjunction with grounding to provide additional protection against voltage surges. SPD are designed to clamp the voltage to a safe level, preventing it from exceeding the equipment's voltage rating. They are typically installed at the service entrance and at critical branch circuits throughout the facility. Grounding also helps to reduce electrical noise and interference, which can affect the performance of sensitive electronic equipment. Electrical noise can be generated by various sources, such as motors, transformers, and electronic devices. This noise can propagate through the electrical system and interfere with the operation of other equipment. Grounding provides a path for this noise to dissipate to Earth, reducing its impact on sensitive equipment. Shielded cables and filters are also used to reduce electrical noise and interference. Shielded cables have a conductive shield that surrounds the conductors, preventing noise from radiating into or out of the cable. Filters are designed to block specific frequencies of noise, preventing them from propagating through the electrical system. In summary, grounding is a critical aspect of electrical system design and is essential for ensuring safety, protecting equipment, and maintaining voltage stability. It provides a low impedance path for fault currents, overvoltages, and electrical noise to dissipate to Earth, minimizing the risk of electric shock, equipment damage, and interference. Neutral, on the other hand, serves as the return path for current in normal operation and is grounded at the service entrance to maintain it at a potential close to Earth potential. Understanding the difference between ground and neutral is crucial for anyone working with electrical systems. Here are a few additional points to consider. Firstly, the size of the grounding conductor is determined by the size of the service entrance conductors. The larger the service entrance conductors, the larger the grounding conductor needs to be. This is because the grounding conductor needs to be able to carry the maximum fault current that could occur. Secondly, the grounding electrode system should be installed in accordance with the NEC. The NEC provides detailed requirements for the installation of grounding electrodes, including the type of electrode, the depth of burial, and the spacing between electrodes. Thirdly, all metal parts of the electrical system should be bonded together. This includes metal conduits, junction boxes, and equipment enclosures. Bonding ensures that all these metal parts are at the same potential, minimizing the risk of shock hazards. Fourthly, surge protective devices should be installed to protect sensitive electronic equipment. SPD are designed to clamp the voltage to a safe level, preventing it from exceeding the equipment's voltage rating. Fifthly, regular inspections and testing of the grounding system should be performed to ensure that it is functioning properly. This includes visual inspections of the grounding conductors and electrodes, as well as testing of the ground resistance. Ground resistance testing measures the resistance of the grounding electrode system to Earth. A low ground resistance is essential for ensuring that fault currents can quickly and safely dissipate to earth. The NEC specifies a maximum ground resistance of 25 ohms for a single grounding electrode. If the ground resistance exceeds 25 ohms, an additional grounding electrode should be installed. Grounding is not a static concept, and its implementation can vary depending on the type of electrical system and the specific application. For example, in sensitive electronic environments such as hospitals or data centers, special grounding techniques are often employed to minimize electrical noise and interference. These techniques may include isolated grounding systems, which separate the grounding conductors for sensitive equipment from the grounding conductors for other equipment. Isolated grounding systems can help to reduce the flow of noise currents through the grounding conductors, improving the performance of sensitive equipment. Another important consideration is the type of grounding system used. There are several different types of grounding systems, including solid grounding, resistance grounding, and impedance grounding. Solid grounding is the most common type of grounding system and is used in most residential and commercial applications. In a solid grounded system, the neutral conductor is directly connected to earth at the service entrance. Resistance grounding is used in some industrial applications where it is desirable to limit the magnitude of ground fault currents. In a resistance grounded system, a resistor is inserted between the neutral conductor and earth. This resistor limits the ground fault current to a predetermined level, reducing the risk of equipment damage. Impedance grounding is similar to resistance grounding, but uses an impedance such as an inductor instead of a resistor. Impedance grounding can provide even greater control over the magnitude of ground fault currents. The choice of grounding system depends on the specific application and the desired level of protection. In addition to the technical aspects of grounding, it is also important to consider the human factors. Electrical safety training is essential for all personnel who work with electrical systems. This training should cover the principles of grounding, the hazards of electricity, and the proper procedures for working safely with electrical equipment. Regular refresher training should also be provided to ensure that personnel stay up to date on the latest safety practices. Furthermore, it is important to promote a culture of safety in the workplace. This includes encouraging employees to report any potential hazards and to take the necessary precautions to protect themselves and others from electrical shock. A strong safety culture can help to prevent accidents and injuries and to ensure the safe operation of electrical systems. In conclusion, grounding and neutral are essential components of electrical systems that play critical roles in safety, equipment protection, and voltage stability. Grounding provides a low impedance path for fault currents, over voltages, and electrical noise to dissipate to earth, while neutral serves as the return path for current in normal operation. Understanding the difference between ground and neutral is crucial for anyone working with electrical systems, and proper implementation of grounding and bonding practices is essential for ensuring the safety and reliability of electrical installations. The NEC provides detailed requirements for grounding and bonding, and compliance with these requirements is essential for ensuring the safety of electrical systems. In addition, electrical safety training and a strong safety culture are essential for preventing accidents and injuries and for promoting the safe operation of electrical systems.